This topic is on stability in discrete systems. Before we start this particular lecture, we know that in continuous time, we are in the S-plane, and for stability in the continuous time, we know that the poles of the system all the poles of the system should be on the left half plane, meaning that the poles should be negative for stability. But in this lecture, we want to consider the stability, how to ascertain the stability in discrete time systems or in the Z-plane. Then we already know this relationship that Z is equal to exponential ST. So this relationship specifies the relationship between the Z-plane and the S-plane. And we know that S is a complex number, and it has the real part given by sigma and the imaginary part given by omega. So substituting this into this relationship, we have this. So the real part is given by exponential sigma t, while the angle is given by simply omega multiplied by t. In the continuous time case, we know that if sigma is equal to 0, that means that you only have imaginary components. And if you have purely imaginary components, that means that there's going to be oscillations, and that's marginal stability, or you are in the unbounded case. And in this case, let's make sigma to be equal to 0. So if sigma is equal to 0 here, so the exponential of 0 is 1. So that means that the modulus of z is equal to 1. So this particular boundary, the magnitude of z is equal to 1. This particular boundary defines the region of marginal stability in the Z-plane. Then the angle is given by omega t, where omega is the angular frequency. So if omega is 2 pi divided by t, then that means that for this, the angle in the Z-plane is translated into 2 pi radians, where 2 pi radians is the circumference of a circle and is 360 degrees. So for the Z-plane, for stability, we want to make sure that the modulus of z is equal to 1 and the angle is also 2 pi. So if we say that the modulus of z is equal to 1, that's the region of marginal stability. So the region of marginal stability, for continuous time, the sigma is equal to 0, and that's marginal stability. But in the Z-plane, the modulus of z is equal to 1, and that's the region of marginal stability. So we know from the continuous time system, when sigma is greater than 0, that means that the poles of the system is positive, is greater than 0. We know that is unstable. For the discrete time case, if the magnitude of z is greater than 1, then we say that the system is unstable. In a continuous time case, if sigma is less than 0, that means that the real part of the pole is negative, is on the left half plane. We know that the system is stable. Then we translate it into in discrete time as the modulus of z being less than 1. So if the modulus of z is less than 1 in the discrete time case, then we say that the system is stable. So this particular graph here we're in continuous time, we're in the S-plane or in the Laplace domain. And here we're in the Z-plane, we're in the discrete time domain. So in the continuous time domain, this line is the region of marginal stability. And we know that when the poles are on the right hand plane, we know that the system is unstable. So this is the then we know that if the poles are on the right half plane, we know that the system is unstable. Then if the poles are on the left half plane, we know that the system is stable. But using this exact transformation relationship, it's this particular line, which is the region of marginal stability, is translated into a circle, the circumference of the circle being 2 pi. The 2 pi radians we mentioned here, and the limit is +1 and -1, because we said that if the modulus of z is greater than 1, that means that the system is unstable. So here is greater than 1, the system is unstable. But if the modulus of z is less than 1, so here we are less than 1, so the system is stable. So in the discrete time domain, or in the z-plane, this particular region of marginal stability is translated into a circle, and the stable region is within this unit circle. So for all values of the poles between, here is +1 and here is -1, here is +1 and here is -1. For all regions within this unit circle, the system is stable in the discrete time case. Then for all regions that lie outside this unit circle, we say that the system is unstable. So that's the relationship between stability in the S-plane and stability in the Z-plane. For stability in the S-plane, you have this line. This is the region of marginal stability. This is the negative side and this is the positive side. So the negative side indicates the region of stability, while the positive side is the region of instability. But in the discrete time domain, we have the unit circle, and previously we're using the modulus of z. So we can say that the region of stability is, if, let me just write it here. So we can define the region of stability as being from -1 less than z less than 1. So z has to be between -1. Here's -1 and here is +1. So we're using the modulus now, but now we're not using the modulus. We are indicating it from -1 to 1. So this is -1 and this is 1 and this is 1 and this is -1. So all the region within this unit circle is stable in the discrete time case. Then the region outside of the unit circle is unstable in the discrete time case. So we've established the relationship between the stable and unstable region in the Z-plane. So I'm going back to 3 lectures we did previously. So we tried to remember that this relationship up here, z is equal to exponential st, is the exact transformation. But in that lecture, if you go back to that particular lecture, we approximated the relationship between the S-plane and the Z-plane using forward rectangular rule. So in the forward rectangular rule, we said that the relationship between the S and the Z is given by this. Then for the backward rectangular rule, we said that the relationship we actually proved this. We said the relationship is given by this. Then for the trapezium rule or the Tonson's rule, the relationship between the S plane and the Z plane, we derived it to be this. Then so if we make Z the subject of formula, you would arrive at this relationship. So is the same thing with what we have up here. The only difference is that here we're making Z the subject of formula in all the three cases. So if you make Z the subject of formula, we're going to arrive at this. Then we add an example in which in the continuous time domain or in the S plane, we got the poles of the system we got was minus 0.2 plus or minus J 0.8. And when we tried to convert, when we try to convert into the Z plane using the forward rectangular rule, if you can remember, this is what we got. Then for the backward rectangular rule, this is what we got. Then for the trapezium rule, we got this. Then for the exact transformation, that's Z is equal to S exponential ST, we got this. Then this particular pole, we're in the S plane, and we already know that when the real part is less than 0, when it's negative, we are stable. Then given the lecture, the brief explanation I gave you in the Z plane, we said that when the pole is within the unit circle being from -1 to 1. If we are in the unit circle, that means that we are stable. So if we look at, and I said that this one is unstable, so I want to show that why this is unstable. So here you have 0.8 and here you have 0.8. So if we were to plot this on the unit circle here, so you know here is 1 and here is 1, then here is -1 and here is -1.
I'll go.
So 0.8 will be here, then on the real part 0.8, then the imaginary part 0.8 will be here. So if you join here, and if you join here and here together, you can see that you are outside of the unit circle. That's why we say that it is unstable, because this is 1 here. So 0.8 will be towards the end, then 0.8 on the imaginary axis is towards this place. Then when you join it together, the point you have here is outside of the unit circle, so it's unstable. So for 0.8 minus J 0.8, so minus 0.8 will be here. So when you trace it here, and you also trace 0.8 here, the point is going to be here, and this is outside the unit circle. So that's why if you go back to the note, we said that this is unstable. So you already know the reason why it's unstable. Then here is, if you plot it on the unit circle, you would say that it is within the unit circle. So 0.58, 0.38. So let me go to the unit circle. Here you have 0.5, which will be around this place. Then 0.3 will be around this place. So the point that it joins is around where my cursor is, and here is within the unit circle. So for the backward rectangular rule, the poles we got are stable poles. Then for the trapezoid rule, this particular one, when you plot it on the unit circle, you will see that is also stable. Then for the exact transformation, this is also stable because 0.5 and 7 plus or minus j 0.59. So 0.57 will be here around this place, and 0.59 will be around this place. Then the point that they join together is within the unit circle, so it's stable. And so we already know how to define stability in the z-plane. So for the z-plane is a unit circle, and the poles should be within the unit circle. And the reason why the results are different is because for the forward rectangular row, the approximation is given by all the shaded region, and this is the line. So for the forward rectangular row, the stability region is given by all of this, and we can see that at some point we are outside of the unit circle. So that's why for forward rectangular row, you can actually have a stable pole or stable poles in the S-plane, but in the Z-plane, it might translate to instability because this is the unit circle we are working with, but this is the range of this line. The shaded region is the range of the forward rectangular row. So that implies that it includes unstable portions also. So that's why at this location, we are having instability because the approximation of the forward rectangular rule is not so exact. So all this region are outside of the unit circle, but the approximation it gives is that of a square. So that's why we have that for forward rectangular rule. For the backward rectangular rule, the approximation it gives is a circle within the unit circle from 0 to +1. So this is the region of stability when it's approximating using the backward rectangular rule. But this is our global region of stability with the unit circle. So the backward rectangular rule is always going to, if in the continuous time case, the system is stable, the backward rectangular rule is going to produce a stable, when you plot it on the z-plane, using the forward rectangular rule, you are going to have a stable pole also. Then for the trapezium rule, if you remember when we did that class, I said that the trapezium approximation is the best approximation. And looking at this figure C, we can see that it approximates the region of stability is exactly within the unit circle. So the conclusion of this is that the trapezium rule gives the best approximation because you are totally within the unit circle. And the forward rectangular rule, when you're converting from the S-plane to the Z-plane, for the forward rectangular rule, if you're in the S-plane, you might have a stable pole, but when you translate it into the Z-plane using forward rectangular rule, it's not guaranteed that you will still be stable because of these regions outside the unit circle that the forward rectangular rule covers, which is unstable. And the backward rectangular rule is going to guarantee stability because the region it approximates is within the unit circle. So if you are stable in the S-plane and you use the backward rectangular rule, definitely you are going to be stable in the Z-plane. Then for the trapezium rule, if you are stable in the S-plane and you use the trapezium rule to approximate the Z into the Z-plane, then definitely you are going to be stable also. And now, this particular part we just covered is when you have poles in the form of this. So just looking at this and we plot it on the unit circle, we can determine if the system is stable or is not stable in the Z-plane. But how about if your poles are in form of a polynomial? For instance, if you have this pole here, and how will you determine if the system is stable or not in the Z-plane? And this is a fourth order polynomial. It's going to be difficult for you breaking it down. So since this is a fourth order polynomial, we are sure that it has 4 poles, but it's not so easy to break it down into those 4 poles. So that's why we need another method. Just by looking at the characteristic equation, we want to be able to know if the system is stable or not when we're in the Z-plane. Then I'm going to be presenting 3 methods: the Routh method, the Jury's method, and the Raible's method. These are the 3 methods I'll be presenting in order to determine the stability in the Z-plane or the stability of discrete time systems. Then this Routh method is familiar because when we did 412, continuous time control system, we encountered the Routh stability criterion. So you can go back to your notes to refresh yourself, but we are going to be using the Routh method. We can extend it to determine the stability of discrete systems, but we are not going to construct the Routh table directly based on this. We are going to apply this transformation first. Then the result we get after applying this transformation, that is what we are going to use to build up the Routh table. So this particular transformation, it follows from this trapezium rule. If you watch both equations, you would observe that they are a little similar. So we apply this transformation to the Z we have here. Then we are going to arrive at another polynomial. The polynomial we arrive at is going to be the polynomial we are going to use to construct the Routh table. So this is the question. So in place of Z, we are going to apply this transformation. We're going to use this. So here, in place of Z, then in place of Z, here. Then we are going to expand the equation. We arrive at this. So this and this are just the same thing. It's just that we separated out the numerator from the denominator. And now we factorize. So we know that omega minus 1 raised to the power 4 is common to all the denominator. So we bring it down here. Then we write another equation of this form. So this equation and this equation are just the same thing. The only difference is that we know that This are the denominator of the five individual fractions we have. Know that this denominator is common to both. So we bring the common denominator out, and we factorize in order to get this. Then when we expand, then when you cross multiply, 0 times omega minus 1 raised to the power 4 is 0. So we just end up with the numerator being equal to 0. And when we bring it out here, you arrive at this. Then when we expand, we just want to simplify things. So if we expand this, we are going to get this. Then when you expand this, you are going to arrive at this equation. When we expand this, we're going to arrive at this equation here. Then we expand this here. Then we arrive at this equation. Then we expand the last term, and we arrive at this. Then when we collect like terms, we arrive at our final equation. So we derived our working equation. So this was the equation. This is the question here. But when we use this transformation, which I've just explained, we arrive at this equation. So it's this equation we are going to use to construct the Routh table. So to refresh your memory from 412, so on this column, you're going to write the quotient. So there's omega 4, omega raised to the power 3, omega squared, and omega raised to the power 1, then omega raised to the power 0 being the last one. Then you're going to put the alternating coefficients of the omegas. So this 2 comes from here. Then you skip this, then you write 26, then you skip this, then you write 4. Then for the next row, you're going to write 14 here. So this is the 14, then the 2, we're going to write it here. Then for the next row, in order to get this row, we multiply this 14 and 26, then you subtract the product of 2 and 2, then you divide by 14, then we arrive at 27.5. Then in order to get the second value here, we multiply this by this, then we multiply this by this, then we subtract the product of this. So here is supposed to be 0. So there should be 0 here. So we subtract the product of 0 and 2. Then we divide by 14. And we arrive at 3.9. So here is 0. Here we give you 0. Because when you multiply 14 times 0 is 0. And also 2 times 0 is 0. So you get 0 here. For the next row, what we do is that we multiply this 25.7 times 2, then you subtract it with the product of 3.9 and 14, then you divide by 25.7, we arrive at this. In order to get this value, you multiply 25.7 times 0, which is 0, then you subtract 0 times 14, which is 0. So here is 0. So I didn't bother to write it. Here we give you 0. For the last row, you multiply minus 0.12 times 3.9, then you subtract 0 times 25.7, then you divide by minus 0.12, you arrive at 3.9. So the others, you're going to get 0 and 0. So if you can remember your 412 in control systems, we said that the system is stable if the the first column, if the elements of the first column have the same sign, if all of them have the same sign, then it's stable. Then if we have a value that has a different sign, then the number of change in signs equals to the number of unstable poles. So here we can see that here we have, here is positive, 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 and here is negative. So definitely this particular system is unstable. Then how many unstable poles do we have? So the number of unstable poles equals to the number of change in signs. So here positive. So here is positive. Then you are changing to positive. So there's no change of sign. So here is positive and you are changing to positive. So no change of sign. But here is positive and you are changing to negative. So we know that we are counting one unstable pole here. Then here is negative and we are changing to positive. So that means that we've counted two unstable poles, because here we change from positive to negative and here we change from negative to positive. So we change signs twice. So that means that the system is unstable and the number of unstable poles is equal to the number of change of signs. So we change signs 2 times. So we have 2 unstable poles. So that's the Routh system in order to determine the stability of a characteristic equation. And it's exactly the same thing in continuous time, but the only difference is that you need to apply this transformation, which is very important. If you just do this exactly, that's not the way to go about it. You first apply this transformation first, then the result you get after applying the transformation, that is what you are going to use to construct the Routh table. Okay, so we move on to the next method. The next method is the Jury's method, and it was developed by Jury and Blanchard. So in this method, we just use the characteristic equation available to us, because we don't want to do the transformation. We don't want to apply any transformation. So in this method, if this is the characteristic equation that is available to you, you're going to use this to construct a table. But the table is the Jury's table and is different in construction. So here is the first value. So you're going to start with, for instance, you're going to start with z raised to power 0. Then you will end with z raised to power n. Then after that, you just put the coefficients directly under. So we know that the coefficient of z raised to power 0 is a0. We know that the coefficient of z raised to power 1 is a1. You know that, then you continue like that. Then you know that the coefficient of z raised to power n is an. So you have an here. So that's for the first row. So you just start with z raised to power 0, then you end at z raised to power n. Then you put the coefficients under. So for the second row, you are going to reverse the ordering of the coefficients. So here we started at a0, a1, a2, then we stopped at an. But now you're going to reverse the direction. You're going to start with an, then you stop at a0. But it's the same, the sequence is the same thing. Then you stop at a0. Then for the third row, you are going to get b0, b1, b2. I'm going to tell you the equation to get the b's. But when you get the b, then for the fourth row, you are going to reverse the direction. You know, here you have b0, then b1, b2, b3 to the last one. And the last one is bn minus 1. So if you have a fourth order polynomial, for the second row, you are going to stop at, if n is equal to 4, for the third row of the b, you're going to stop at 3. Then for the fourth row, just reverse the direction. So here you are starting from B0 and you're ending at Bn minus 1. For the fourth row, you will start at Bn minus 1 and you will stop at B0. So just reverse the direction. Then you calculate the C. I'm going to give the equation to calculate the C shortly. But when you calculate the C, you start at C0, then you end at Cn minus 2. So if n is equal to 4, you're going to stop at Cn minus 2. So 4 minus 2 is C2. So you're going to stop at C2. So that's for the fifth row. Then for the sixth row, you reverse the direction of the C. So you're starting at Cn minus 2, then you're stopping at C0. Then this is the way you construct the table. Then this is the formula you use to get the B row. Then this is the formula in which you use to get the C row. So for the B row is the magnitude or the determinant of this. So we have BK here. So K is from 0 to n minus 1. Then you have I here. I is from 0 to n minus 2. So if you want to calculate B0, for instance, or B0, so here is A0, then here is AN. So because we want to calculate B0 is n minus 0, and here will be A0. So if it was B1 wanted to calculate,